This is the question from GATE 2006. The question is, under low level injection assumption, the injected minority carrier current for an extrinsic semiconductor is essentially the options are A, diffusion current, B, drift current, C, recombination current, D, induced current. So here is the question, and we should understand the statement first, and then we will go for the option. In this question, the statement that has to be underlined here is injected minority carrier current. What is the meaning of this statement first? Injected minority carrier current means the current which is, it is the process in which the current is injected into a extrinsic semiconductor, and this injected current is nothing but the current due to minority charge carrier. So injected minority carrier current is nothing but the process in which the minority charge carrier is injected into a extrinsic semiconductor. So likewise, if you say doping is the process in which the majority carrier is added into a intrinsic semiconductor, and it is the process in which the minority carrier are injected into an extrinsic semiconductor. So what is the difference? Doping is the process. It is the process in which the majority carrier is added in intrinsic semiconductor. And injected minority carrier current, it is the process in this process we are adding the minority carriers in extrinsic semiconductor. So this is the difference between doping and minority carrier injection. So how we are doing this? First of all, we have to understand this thing. So suppose we are taking an extrinsic semiconductor, and suppose this semiconductor is of N type. So we are taken an extrinsic semiconductor, and suppose this semiconductor is of N type, then if initially we have the concentration of this electron, that is the majority charge carrier inside this semiconductor, is throughout this semiconductor. Suppose we are taking from x is equal to 0 to x is equal to L, the length of the semiconductor. So throughout the length of the semiconductor, the concentration of majority charge carrier, suppose we are taking this is equal to Nd. That means if it is uniformly doped, then throughout the semiconductor we have the Nd atoms. This is the atoms, that is nothing but the donor atoms which is added inside this semiconductor. And if you consider the minority charge carrier inside this one, the minority charge carrier is very less because it is an N-type semiconductor. So here the minority charge carrier is holes in N-type semiconductor, which is represented by Pn naught, and this is Pn naught, this is Pn naught, this is Pn naught. That means from length x is equal to 0 to x is equal to L, throughout the semiconductor, the concentration of majority charge carrier Nd and the concentration of minority charge carrier Pn naught is constant throughout the semiconductor. So how to find out this concentration of minority charge carrier, and how we are saying that this minority charge carrier is constant throughout the semiconductor? So we can use mass action law for that. By using mass action law, we can say that the number of electrons, multiplication of number of electrons with holes is constant, and this constant this constant is nothing but the square of intrinsic concentration, which is a constant value at a particular temperature or at a thermal equilibrium. So we can say this is suppose n type का semiconductor, then we can say this is n in n type and this p in n type, and this is equal to ni square. So we are going on finding out the concentration of minority charge carrier in n-type semiconductor. This is equal to ni square divided by n in n-type, and this n in n-type is approximately equal to the number of donor atoms added. So this is equal to ni square divided by nd. Since we know that in a particular semiconductor the value of this ni square and this nd are constant, so we can say that the concentration of minority charge carrier, that is in n-type it is holes, the concentration of holes in n-type semiconductor, and this not represent the thermal equilibrium. At thermal equilibrium it is constant. So that's why we have taken that in an n-type semiconductor the concentration of minority charge carrier is constant throughout the semiconductor, and in a uniformly doped semiconductor the concentration of majority charge carrier, that is nothing but the donor atom concentration, is constant throughout the semiconductor. Now when this minority charge carrier is changing inside the semiconductor, or what is the meaning of this minority carrier injection? So suppose now the same semiconductor we are taking like this is n-type semiconductor, and suppose we are illuminating at x is equal to 0 and this is x is equal to L. Suppose we are illuminated this semiconductor at x is equal to 0 with some light source. Suppose this is the light source which is illuminated at one end of the semiconductor at x is equal to 0. So this is what? This is actually a light source. So because of this light source, what will happen? The covalent bond at the corner, at this edge of the semiconductor, will get broken down, and because of this breaking of covalent bond, what will happen? The number of donor atoms at this semiconductor increases. That means suppose the incremental amount of donor atoms is suppose delta, and similarly since the covalent bond is broken, we have the same incremental value of this minority charge carrier inside the semiconductor. What is the reason behind this same increment? Because we know that generation is the process. Generation is the process in which the number of charge carrier, that is minority and majority charge carrier, both will increase, and the number of charge carrier increase is same, that is if delta is the incremental value of the minority charge carrier, and the same amount of delta is incremented in majority charge carrier. So majority charge carrier. So generation is the process in which we are getting one majority and minority charge carrier, one electron hole pair. So it is also represented as electron hole pair generation. So we are getting the same, that is delta here. This is the incremental value of minority and majority charge carrier. And similarly we are, if you move towards x is equal to L, we are getting the same values since we are illuminated only one surface, one edge of the semiconductor, so only covalent bond is broken at this edge of the semiconductor, and we are assuming that the remaining values will be getting same like this. Now both majority and minority has increased inside this semiconductor. Now we are comparing. Since Nd is very much greater because it is the majority charge carrier, Nd is very high, and if you are added a small amount of donor atom in this is taken as negligible for a very high ND value, this is taken as negligible, and if it is negligible, we are getting the same amount of donor atoms, that is approximately same amount of donor atoms, that is ND plus delta is equal to ND. But since the minority charge carrier is very less in an N-type semiconductor, which is hole here, and if you are added a small amount in a small amount, then this is always, we cannot neglect this particular value, that is delta value here. So we have to consider Pn naught plus delta n here. So I am taking the same thing, because since it is negligible, we are neglected this amount. So we can see that this is the minority charge carrier which has increased, and this is increased by delta n at one end of the semiconductor. And since we know that, now we can see from this diagram that the minority charge carrier is increased at one end, and at the infinite end of this semiconductor, the minority charge carrier is same as we have taken initially when it is at thermal equilibrium. That means when there is no light source is illuminated. So if you show this one in a diagram, that if you are representing this one as concentration of minority charge carrier, that is Pn, and this is at x is equal to 0, and suppose we are taking this one as length, this is taken as concentration, and initially the concentration will be Pn naught, and we have increased the concentration by delta amount. So the total concentration at this point is suppose Pn naught plus delta. And on the other end of this semiconductor at x is equal to L, suppose we have taken the concentration is same, and this is equal to Pn naught. So here at one edge of the semiconductor x is equal to 0, the concentration is increased, and at the other end of the semiconductor, that is suppose we are taking at infinite end, the concentration will be Pn naught. Then what will happen? Since we know that every particle will move from higher concentration to lower concentration, that means this Pn naught, that is the minority charge carrier, Pn naught plus delta amount will tries to move from this higher concentration to a lower concentration value from x is equal to 0 to x is equal to L. So this movement of charge carrier is because of diffusion. This movement of charge carrier is because of diffusion, because we know diffusion is the process in which the charge carrier, either it is majority or minority, it will always moves from higher concentration to lower concentration region. So in this question we have 4 options, and those 4 options are, this is diffusion current, drift current, recombination current, and induced current. So the minority carrier current is because of diffusion current, because if one edge of the semiconductor is illuminated with some light source, then definitely the minority charge carrier is increased at one end of the semiconductor at its x is equal to 0, and it will move to the other end. The reason of movement of charge carrier is nothing but diffusion. So diffusion is the process by which we can move the minority charge carrier from one end to other end. So this can also be understood by one example. Suppose we have a bucket, and in this bucket we have a full bucket is filled with water, and if you add a drop of ink in this bucket, then in this water is the majority. If you suppose like this, the water is the majority charge carrier and this drop of ink is the minority charge carrier. So this minority charge carrier, initially it is dropped at one end, then after some time it will be distributed throughout this one, and this distribution is because of diffusion. And the same reason is applied here, and we have the correct option, that is nothing but the diffusion. This is the question from GATE 2014 and set 2. The question is, A silicon bar is doped with donor impurities and D is equal to 2.25 into 10 to the power 15 atoms per centimeter cube. Given the intrinsic carrier concentration of silicon at T is equal to 300 Kelvin is Ni is equal to 1.5 into 10 to the power 10 per centimeter cube. Assuming complete impurity ionization, the equilibrium electron and hole concentration are: option A is N0 is equal to 1.5 into 10 to the power 16 per centimeter cube. P0 is equal to 1.5 into 10 to the power 5 per centimeter cube. B option is N0 is equal to 1.5 into 10 to the power 10 per centimeter cube and P0 is equal to 1.5 into 10 to the power 15 per centimeter cube. C option is N0 is equal to 2.25 into 10 to the power 15 per centimeter cube and P0 is equal to 1.5 into 10 to the power 10 per centimeter cube. D option is N0 is equal to 2.25 into 10 to the power 15 per centimeter cube and P0 is equal to 1 into 10 to the power 5 per centimeter cube. So this is the question, and in this question it is given that a silicon bar is doped with donor atoms, and this is the concentration of donor atoms which has been added in the silicon bar, and this is the intrinsic concentration which is given. And in this question one assumption is given, that is complete impurity ionization. And in this question two things has been asked. The first is electron concentration, that is N0, and this is question mark, and the whole concentration which is represented by P0, this is question mark. So first thing is that we have to assume a silicon bar. So in this we have a silicon semiconductor, that is intrinsic semiconductor, and in this silicon if donor atoms is added like this, if donor atom is added, the resultant semiconductor is nothing but an N-type semiconductor bar. So in an N-type semiconductor bar, the majority charge carrier is nothing but the electrons. Here it is electrons. The majority charge carrier is electrons, and this electron is represented by N, and since it is an N-type semiconductor, that is given by N with subscript N. And now comes here the meaning of this word, that is complete impurity ionization. Complete impurity ionization means each and every donor atoms will contribute one electron to its semiconductor. So each and every donor atoms, if it contributes one electron to the semiconductor, the number of electrons in an N-type semiconductor is equal to the number of donor atoms, because complete impurity ionization. And it is given here, this is equal to 2.25 into 10 to the power 15 atoms per centimeter cube, and D is given. So the answer for this number of electrons is equal to, this is equal to N in N-type semiconductor, and this is equal to 2.25 into 10 to the power 15 per centimeter cube. This is the first answer for this question. Now, for finding out the minority, since majority charge carrier is electron, we can say the minority charge carriers in N-type semiconductor is nothing but holes. In N-type semiconductor is nothing but holes. And to find out the hole concentration, that means the holes in N-type semiconductor. And the holes in an N-type semiconductor, in this question it is represented by P0, and we have to find out this value. This is question mark. That means we have to find out minority charge carrier concentration. For finding out the minority charge carrier concentration, we can use mass action law. what is mass action law? Mass action law, the statement is the product of holes and electrons in a semiconductor is constant, and this constant is nothing but the square of intrinsic concentration. So, since it is a n-type semiconductor, this is a n-type semiconductor, so we can write this is P in n-type semiconductor and N in n-type semiconductor, this is equal to Ni square. So, this P in n-type semiconductor in our question it is represented by P naught, so this is equal to P naught, and N in n-type semiconductor is represented by N naught, and this is equal to Ni square. So, here Ni square, the Ni value is given in the question and it is equal to 1.5 into 10 to the power of 10 for silicon and square of this one. And we have to find out the value of P naught, so we have to divide this with N naught. So, what is N naught value here? N naught is equal to 2.25 into 10 to the power 15 per centimeter cube. So, we can apply this one, this is P naught is equal to, so here I am writing this is 1.5 into 10 to the power 10, the square of this one divided by 2.25 into 10 to the power 15. And if it is taken square of this one, this is equal to 2.25 into 10 to the power 20 divided by 2.25 into 10 to the power 15. And the answer will be, this is equal to 1 into 10 to the power 5 per centimeter cube. And this is the correct answer. So, in option D, it is given that electron concentration, that is N naught, is equal to 2.5 into 10 to the power 15 per centimeter cube, and the whole concentration P naught is equal to 1 into 10 to the power 5 per centimeter cube. And this is the correct answer for this question. This is the question from GATE 2014, set 4. The question is, an n-type semiconductor having uniform doping is biased as shown in the figure. If EC is the lowest energy level of the conduction band, EV is the highest energy level of the valence band, and EF is the Fermi level, which one of the following represents the energy band diagram for the biased n-type semiconductor? There are 4 options given in diagram, so we will consider this in the discussion. So, this is the diagram given in the question. In this we have an n-type semiconductor which has the majority charge carrier electron and the minority charge carrier holes. And in this semiconductor, a 5 volt DC voltage is applied, which has the polarity on right side positive and left side negative. And in this semiconductor, if this polarity is considered, we can assume that on the right side the 5 volt is applied, and with respect to this 5 volt, if the left side is considered, it is maybe taken as 0 volt. That means we can say this 5 volt is uniformly distributed through the length of the semiconductor. If 5 volt is uniformly distributed through the length of the semiconductor, then we can say at the center of this semiconductor we may have the voltage that may be equal to 2.5 volt. So, likewise the whole 5 volt is distributed in this semiconductor, which has the lowest magnitude on left side and the highest magnitude on right side. So, because of this positive polarity which is shown in the question, because of this positive polarity when applied to the right side, and we have the semiconductor which is n-type, that means this semiconductor is reverse biased, and it is more reverse biased on right side and it is less reverse biased on left side. So, I am writing here in this semiconductor, because of this 5 volt and it is n-type and positive polarity, 5 volt n-type positive polarity on right side, that means N-type semiconductor, when positive polarity is applied, it is reverse bias. This is reverse biased. And on the left side, if you consider, we have 0 volt. So if you compare right and left side both at a time, this is reverse biased and it is considered to be more reverse biased. And on the right side, we can consider this is less reverse biased. So this is the conclusion from the question. Now come to the options of this question. There are 4 options which is given in this question. The options in these questions are A, B, C, D. We can see the diagram. According to the diagram, the representation EC is the lowest energy level of the conduction band, EF is the Fermi energy level, and EV is the highest energy level of the valence band. So we have 4 different shapes, and according to the shapes, we have to find out which is the correct option for this question. So before starting with a N-type semiconductor, we are considering a P-N junction, and after a while we will come to consider only N region of a P-N junction, because if you take P-N junction and understand it clearly, then it is very easier to consider only one side of the semiconductor and get the correct answer. So that's why we are starting with a P-N junction. So I have drawn a P-N junction here for the solution, and this is P and this is N-type. That means here we have majority charge carrier holes and here we have majority charge carrier electrons. So as we know that in a P-N junction, the Fermi level throughout the semiconductor is constant. So if you take the diagram, this is the energy level. If you consider y-axis as the energy and x-axis as distance, we can see the diagram, the same diagram can be represented in terms of energy levels. So if you take this semiconductor in terms of energy level, this is the width of the depletion region. So I have taken this width of the depletion region, and I suppose that the width of the depletion region is negligible for this P-N junction semiconductor. So the same thing I have drawn here. This is Fermi energy level which is constant throughout the semiconductor. I have drawn the same thing. This is the Fermi energy level which is constant throughout the semiconductor. And since we know for a P-type semiconductor, the highest energy level of the valence band is nearer to the Fermi energy level of P-type semiconductor. So this is the highest energy level of the valence band which is nearest to this Fermi energy level. And in the same P-type semiconductor, the conduction band is far away from this Fermi energy level. So we can see here, according to this diagram, this is the lowest energy level of the conduction band which is far away from this Fermi energy level. The same thing is drawn here, but here the condition is that the lowest energy level of the conduction band is nearer to the Fermi energy level, and the highest energy level of the valence band is far away from this Fermi energy level. So we have the diagram in this way. This Fermi energy level is because the presence of electron in a particular band. So according to that, we have this Fermi energy level concepts. So since in N-type semiconductor, we have free electrons which is present in the conduction band, and in P-type semiconductor, we have the holes which is majority charge carrier. That means the bonded electrons is present, and where the electrons is present, the Fermi energy level will lie nearer to that. So here the holes is nothing but the bonded electrons. Because of this bonded electron, Fermi energy level is present nearer to this valence band, and because of free electrons in the N-type semiconductor, the Fermi energy level lie nearer to the conduction band. So I am drawing the same thing. Suppose this is a free electron which is present in the conduction band, free electron. So I have not applied any external potential. I have not applied any external potential to this semiconductor. That means this semiconductor is a open circuited one. So now if this electron move from this part of the semiconductor from the N region to P region, that means this free electron will have to be free on the other side also. So if this electron moves to the valence band on the other side, this is bonded one. So this electron when moves to the p side, then it has to take a jump from this part to this part, and now this electron is again in the conduction band, and since we know that free electrons always present in the conduction band, so this is the jump of the free electron from one part, that is n side, to the p side. So when the electron jumps from this side to this side, it has to cross the difference in energy level, which is the difference between the lowest energy level on n side of the conduction band to the lowest energy level of p side on the conduction band. So we have to take the difference. That means this electron has to have this much amount of energy to cross from n side to p side. So if you take the energy difference can be represented by, this is ECP minus ECN. That is the lowest energy level of the conduction band on p side and the lowest energy level of the conduction band on n side, and this is equal to the difference between these two energy level, and which is known as the contact difference of potential, which is also known as built-in potential. So I am writing this is equal to the built-in and this is represented by VBI. So again, if you take the same thing for this side, and since we know that in p side the holes are the majority charge carrier, and suppose this is the holes which is having this, and suppose this hole if move from p side to n side, then it has to be moved from the lowest energy level on p side, that is the valence band, to the other side, because it cannot move to the conduction band, because in the conduction band only free electrons in present, and we have considered here hole. So this hole has to move from this side to this side when it moves from the valence band on one side to the valence band on other side. And since we know that holes never moves, then definitely we have to consider that the bonded electron on one side of this semiconductor, the bonded electron, if the hole is moving on this direction, then definitely the electrons will move from this to this. So this is the electron which is moving from the right side to the left side, that means from n to p. And again it has to cross the built-in potential, and here the built-in potential can be represented by EVP minus EVN, and this is also built-in potential, that is represented by VBI. That means when the electron is moving from this side to this side, or the hole is moving from this side to this side, always we have to cross, or this electron should have this much amount of voltage to move from this side to this side, or this much amount of energy to move from this side to this side. So since in our question, if you see here, in our question the circuit is not open circuited, that means the given sample is not open circuited. If it is not open circuited, then we have to apply some external potential. So in this question also we can apply some external potential, and this external potential may be in forward bias mode or maybe in reverse bias mode, both we can consider. So as we know that if we apply forward bias to this PN junction diode, then definitely this built-in potential, that means the difference in potential between these two levels of the energy will reduce, and if we apply reverse bias to this PN junction, then the difference between these two levels will increase. So if you increase, suppose we can say that we are considering one by one. For forward bias, the difference between these two, suppose we are considering this energy level, the difference between conduction band on both sides. So this is ECP when we are considering the forward bias mode, that is represented by FB, ECP minus ECN. This difference will have to be reduced. Since because of forward bias, the potential difference should reduce. So if it is reducing, what does it mean? This ECP will move down and this ECN will move upward. That means the energy, the conduction band energy will move up if we are considering the forward bias. So I am writing here in a statement the ECN for forward biasing, the energy conduction band, the lowest energy level of the conduction band in N-type semiconductor will move up. And suppose we are, since I am considering here only N-type because the question is of N-type semiconductor only. And suppose we are providing a reverse bias to this diode, then PN junction diode, then we can write this ECP minus ECN, the difference in energy between the P side and N side, the lowest energy level of the conduction band will, if it is reducing, then the height of potential barrier will increase. That means the built-in potential will get increased. So if it is increasing, I can write this will move up and this will move down. So I am considering only N side. So here the ECN, here the ECN will move down. So from this following discussion, we come to know that when it is forward bias, the ECN will move up, and when it is reverse bias, the ECN will move down. That means in our question, if you see that in N-type semiconductor, we have seen that this is more reverse biased and this is less reverse biased. So both sides are reverse biased. That means we have to consider this line only. Because this is reverse bias, we have to consider this line only. So whenever the semiconductor is more reverse biased, when it is more reverse biased, then what will happen? The conduction level energy, that is lowest energy level of conduction band, which is represented by ECN, will move down. ECN will move down, and here also the ECN will move down, because here also we have considered the reverse biasing, here also we have considered the reverse biasing. Both the cases are having reverse biasing, but it is more reverse bias, it is less reverse bias. So this side the energy level, the conduction band energy level will move down, and this side also the conduction band energy level will move down, but here the movement will be large, but here the amount of movement of conduction band is less. So here the amount of movement of ECN is large, and here if you see this amount of movement of ECN is less. So now according to discussion, come to the options. Initially we have seen the first option. In this we have Fermi energy level which is constant throughout the semiconductor, and there is no movement, it is like this. That means there is no movement of conduction band or valence band. And in the second option we can see that Fermi energy level will move down, but the EC, the conduction, the lowest energy level of conduction band here it is never moved. So in third option we can see it is moving in this direction, that is on left side it is more movement of conduction band, and here we can see the less movement of conduction band. But in our discussion we come to the conclusion that on right side the amount of movement should be large, and on left side the amount of movement should be less. And come to the fourth option, we can see on right side the amount of the movement of conduction band is large, and on the left side the amount of movement of conduction band is less. That means this fourth option, the D option, is the correct option, and this is the correct answer for this question. This is the question from GATE 2015 set 2. The question is, a DC voltage of 10 volt is applied across an N-type silicon bar having a rectangular cross section and length of 1 centimeter as shown in the figure. The donor doping concentration Nd and the mobility of electrons mu n are 10 to the power 16 per centimeter cube and 1000 centimeter square per volt second respectively. The average time in microsecond taken by the electrons to move one end of the bar to another end is, fill in the blanks. So according to the question, this is the diagram which is given in the question, and in this diagram we have an N-type silicon bar which has a length of 1 centimeter, and it is given that its cross section is square, and in this semiconductor bar a constant voltage of 10 volt is applied, and the polarity of this 10 volt is negative on right side and positive on left side. So the given question is this, and the given data is length of the semiconductor is 1 centimeter, Nd is equal to 10 to the power 16 per centimeter cube, and mu n is equal to 1000 centimeter square per volt second. So according to this question, when a constant voltage of DC 10 volt is applied to N-type silicon bar, because of this negative polarity on right side, the electrons, which is the majority charge carrier inside this semiconductor bar, will move towards the left side. So the electrons in this will be moving towards this side. This is the movement of electrons in the semiconductor bar. So in this question, the question is that what is the time, that is the time needed by the electron to move from one end of the semiconductor, that is for this end, from this end to the another end of the semiconductor to this end. That means we have to find out this movement of electron is actually called transit time. That means we have to find out the transit time, and the definition of transit time is that the time required by an electron to move from one end of the semiconductor to another end. So we have to find out this time, and this is represented by tau. So tau, we have to find out this tau. So from the basic physics we know that if you find out the distance traveled by any object is equal to the distance is equal to the velocity into the time. So in this question we have to take the same basic physics fundamental equation, and we have to find out the time, and this time is equal to the distance traveled by the object and divided by the velocity. So same here, we have to apply the same formula here. Here the distance travel is nothing but the length of the semiconductor, suppose it is represented by L. So this is equal to the length of the semiconductor, which is L, divided by the, since we have applied a constant DC voltage, and because of this constant DC voltage the electrons will access some drift velocity. So we have to take this formula and we have to apply here the drift velocity. So this is the formula. By this formula we have to find out the transit time of this question, and we have to find out this in a microsecond unit. So directly we can use this formula, and I am using the same thing. The transit time tau is equal to length divided by drift velocity, and which is represented by V with subscript D. And from the fundamental we know that mobility of any electrons or holes is equal to the drift velocity per unit applied electric field. This is the formula which has to be used here. So here we have to use the formula for this drift velocity, and drift velocity is equal to the mobility of electrons into the electric field. So I am using this by replacing this drift velocity from here, and this is equal to the mobility of electron into the electric field applied. Here, in spite of this electric field, we have the voltage that is constant DC voltage 10 volt. So we can use this one here. This is length divided by the mobility, and since we know the relationship between the electric field and the voltage, so we can use that one. This is equal to voltage applied divided by the length of the semiconductor. So by using this one, we can extend it, and this is L square divided by mu n into the voltage applied. So the length of the semiconductor is given, that is equal to 1 centimeter, the square of this 1 centimeter, and the mobility which is given here, that is equal to 1000 centimeter square per volt second, and the drift and the voltage that has been applied here, this is 10 volt. So if you take this one, and if you find out this one in terms of microsecond, this is equal to 100 microsecond. So this is the answer of this question. This is the question from GATE 2016, set 1. The question is, consider a silicon sample at T is equal to 300 degree Kelvin with a uniform donut density Nd is equal to 5 into 10 to the power 16 per centimeter cube, illuminated uniformly such that the optical generation rate is G optical is equal to 1.5 into 10 to the power 20 per centimeter cube per second. Throughout the sample, the incident radiation is turned off at T is equal to 0. Assume low level injection to be valid and ignore surface effects. The carrier lifetime are tau p naught is equal to 0.1 microsecond and tau n naught is equal to 0.5 microsecond. The diagram is given in the question. We have to find out the whole concentration at T is equal to 0 and the whole concentration at T is equal to 0.3 microsecond respectively are. There are 4 options. Option 1 is 1.5 into 10 to the power 13 per centimeter cube and 7.47 into 10 to the power 11 per centimeter cube. Option B is 1.5 into 10 to the power 13 per centimeter cube and 8.23 into 10 to the power 11 per centimeter cube. Option C is 7.5 into 10 to the power 13 per centimeter cube and 3.73 into 10 to the power 11 per centimeter cube. And option D is 7.5 into 10 to the power 13 per centimeter cube and 4.12 into 10 to the power 11 per centimeter cube. Here is the diagram which is given in the question. This is an N-type silicon bar which is illuminated with light, and these are the given condition. We have to find out the whole concentration at T is equal to 0 second and at T is equal to 0.3 microsecond. Actually, this is the question from the minority carrier injection. Minority carrier injection means when a semiconductor bar is illuminated with light at any surface. Suppose this is the surface on which we are illuminating the semiconductor with light. Then suppose this is an N-type semiconductor. So when this is illuminated with light, and if you consider with respect to time, suppose this is the time. So when this semiconductor is illuminated with light at T is equal to T dash time, then what will happen inside this semiconductor? The carrier generation starts, and in this carrier generation, both majority and minority both will start generating. And if you consider this is an N-type semiconductor, that means electrons and holes both are generated inside this semiconductor, because generation is the process in which we are getting an electron hole pair, and in this we have both electrons and holes both are generating, and this electron is the majority charge carrier. This electron is the majority charge carrier, and this holes, that is P, is the minority charge carrier. So this is the question from the minority carrier injection, because if in a semiconductor, if you are illuminated with light, then the generation rate of minority charge carrier is very much greater than the generation rate of majority charge carrier. So we cannot have a significant effect of change in the concentration of majority charge carrier if you compare the change in concentration of minority charge carrier. That means we can always have an effect of change of minority charge carrier in dominant way in comparison with change in majority charge carrier. So the same thing, if it is represented in graph, then we can have the graph like this. And in this graph, if you understand the basics thing, suppose I am representing with respect to time, suppose this is the time t is equal to t dash, when the semiconductor is illuminated with light. So I am representing here the light, this is on. And in the question given that at t is equal to 0, suppose this is the time at t is equal to 0, when the light is off. And if you see one by one how the graph is working, see this y-axis is taken is the total concentration of holes in an n-type semiconductor, and this x-axis represents the time. So suppose at time t is equal to t dash, this is the time when the concentration will get changed. And before the time, this n-type semiconductor is having the minority charge carrier, and it is called minority charge carrier at thermal equilibrium. That means when no external light source is applied to this semiconductor, and here is the reason, when no light source is applied to the semiconductor, that means at this time the concentration of holes in the semiconductor is represented by this Pn naught. What does it mean? It is the holes concentration in n-type semiconductor at thermal equilibrium. So initially the concentration of holes in n-type semiconductor is this much. This is the concentration of holes in n-type semiconductor. Suppose at time t is equal to t dash, which is represented here, the semiconductor is illuminated with light. Suppose this is at time t is equal to t dash, the semiconductor is illuminated with light. And when the semiconductor is illuminated with light, the concentration of minority charge carrier, which is represented here, is increasing, and this is the change in concentration of minority charge carrier which is shown here. And this is the change in minority. Initially it will start like this and it will go like this. It is the saturation point. And suppose in the question it is given that at t is equal to 0 time, the illuminated light is switched off. And when the illuminated light is switched off, we know from the basic semiconductor that the recombination of minority charge carrier will start, and because of this recombination we are losing one electron hole pair. So for every recombination we are losing electron hole pair, that means the concentration will decrease exponentially, and this is the graph which shows the decreasing of concentration of holes in an n-type semiconductor, which is decreasing exponentially. So if you consider at t is equal to 0 time, when time t is equal to 0, the total concentration of the holes in an n-type semiconductor is the summation of this much quantity and this quantity, where this p dash n at 0 is nothing but the concentration of holes, and it is at time t is equal to 0. But this concentration is the excess concentration. Why it is called excess concentration? Because it is the concentration which changes because of illuminated light. And second thing, if you see this one, this is the concentration at thermal equilibrium. So we can write one by one. So here we can have this Pn naught, which is the concentration of holes. Initially, how much holes are present? This is the concentration of holes at thermal equilibrium. That means the initial holes concentration. And if you write the second one, that is Pn of t, P dash n of t, and this is the concentration. We can write directly the excess concentration. This is the concentration of holes when light is illuminated. This is the excess concentration. And from the graph we can see the total concentration, suppose we are considering at time t is equal to 0, the total concentration at time t is equal to 0 is represented by P dash n of 0 is equal to the summation of the concentration at thermal equilibrium P dash n of 0 plus the excess concentration P dash n, and it is at time t is equal to 0. This is the total concentration in the semiconductor of holes at time t is equal to 0. Then what is the concentration at any time? That means at any time, suppose we are taking t, and we can represent here also, suppose at any time t, what is the concentration? So from this we can see that any time t, the concentration, the total concentration is the summation of the initial concentration Pn naught plus the excess concentration, this amount. So we can write here, the at any time t, the total concentration is represented by Pnt. This is the summation of the initial concentration Pn naught plus the concentration at any time t. And the concentration at any time t, since we can see this is exponentially decreasing, so we have this equation, that is, this is Pn naught, the initial concentration, plus P dash n of 0, that is the concentration at time t is equal to 0. This is excess concentration at time t is equal to 0 into e raised to minus t divided by tau p. This is the equation which can be used to find out the concentration of holes at any time t. So now see what is asked in the question. In this question, the question is asked that what is the concentration of holes at time t is equal to 0 and at time t is equal to 0.3 microsecond. So we can write this one. Since we have the equation, what is the concentration of holes at time t is equal to 0. So this dash should not be there. And what is the concentration of holes at any time? So we have the two equation, that is the total concentration of holes in n-type semiconductor at time t is equal to 0. This is nothing but the initial concentration Pn naught plus the concentration of holes at time t is equal to the excess concentration of holes at time t is equal to 0. This is the concentration t is equal to 0 second. The total concentration of holes at time t is equal to 0 second. And the second is what is the total concentration at time t is equal to, this is question mark, we have to find out this one, and this is 0.3 second, sorry microsecond, 0.3 microsecond. So this is equal to P, the holes concentration at any time t, here time is equal to 0.3 microsecond. We have to consider this one. So we know that at any time t, the total concentration of holes is equal to the initial concentration plus the excess concentration, which is represented by Pn, P dash n of t. And we know that this is initial concentration plus P dash of the concentration of holes Pn of dash, Pn dash at 0 into e raised to minus t divided by tau p. So these two are the formulas. This is first formula and this is second formula, by which we can find out the concentration of holes at time t is equal to 0 and time t is equal to 3 microsecond. Now first of all find out this one. From mass action law, we know that the multiplication of concentration of holes, that is P, with electrons n is always constant, and this constant is nothing but the square of the intrinsic concentration. So by this equation, we can find out the Pn naught value. Since we have considered this semiconductor is of n type, so the same equation, the mass action law same equation can be applied to n type semiconductor. So this is Pn and this is Nn and this is equal to Ni square. And we know, since we are finding out the value at initially, that is at thermal equilibrium, and this is nothing but Ni square divided by the concentration of holes electrons in an n-type semiconductor, and this is equal to Ni square divided by Nn is nothing but Nd. And since we know that for a silicon, this semiconductor is silicon, since we know that the Ni is equal to 1.5 into 10 to the power 10. This is the constant value, which always we have to remember this value, and this is the square of this one, and Nd value is given in the question, and that is 5 into 10 to the power 16. So we can apply this one. This is equal to 5 into 10 to the power 16. And after doing the calculation, we have the answer, and the answer is 0.45 into 10 to the power 4 per centimeter cube. So on this equation, we got this value. This is equal to 0.45 into 10 to the power 4 per centimeter cube. Now we have to find out this value to find out what is the total concentration at t is equal to 0 second. So for finding out this excess minority carrier concentration, that is P dash n of 0, we can use the generation rate which is given in the question, that is G opt into the carrier lifetime, that is tau, and this is for p-type semiconductor, it is given here. This is equal to Tp naught is equal to 0.1 microsecond. So this is equal to Tp naught, which is given here 0.1 microsecond, and both this value is given in the question. We can see here this is equal to 1.5 into 10 to the power 20, and this is equal to 0.1 microsecond, and if you multiply these two, we are getting the answer, that is equal to 1.5 into 10 to the power 13 per centimeter cube. This is the correct answer. And we have got both these values. This one, this is equal to 0.45 into 10 to the power 4 per centimeter cube, and this is equal to 1.5 into 10 to the power 13 per centimeter cube. So if you want to find out this value, that is Pn at 0, that is the concentration of holes in n-type semiconductor at time t is equal to 0. This is equal to the initial concentration, that is concentration at thermal equilibrium, plus the excess concentration, and it is at time t is equal to 0. So if you add these two, this is equal to 0.45 into 10 to the power 4, and this is addition of this value, that is second one 1.5 into 10 to the power 13, and the answer approximately by adding these two will give, that is Pn naught is equal to 1.5 into 10 to the power 13 per centimeter cube, and this is the approximate value of this addition. So this is the first option we got from the calculation. That means we have got this value, and this is equal to 1.5 into 10 to the power 13 per centimeter cube. This is the concentration of holes in n-type semiconductor at time t is equal to 0. The first questions we got. Now we have to find out the concentration of holes at time t is equal to 0.3 microsecond. For this we have this formula, and we are using time t is equal to 0.3 microsecond, and for this we have used this formula, that is concentration of holes in n-type semiconductor at 0.3 into 10 to the power minus 6, because it is given in microsecond, and this is equal to the initial concentration plus the excess concentration, and which has the formula, this is P dash n of 0 e raised to minus t divided by tau p, where tau p is the carrier lifetime, hole's carrier lifetime. This is Pn naught, we have the value initially, this is 0.45 into 10 to the power 4, and P dash n of 0, we have this formula, this value, and this is equal to 1.5 into 10 to the power 13, and this is exponential value of minus t. T is here 0.3 into 10 to the power minus 6. So this is equal to 0.3 into 10 to the power of minus 6 divided by tau p naught. This is naught which is given in the question here. We have this is equal to tau p naught, this is equal to 0.1 microsecond. So we can apply this formula here, this is equal to 0.1 into 10 to the power minus 6. And after calculation we can have the correct answer, which is equal to 7.47 into 10 to the power 15 per centimeter cube. And this will be the correct answer of this question. Hence we have two answers, that is this one and this one, and this will be the correct answer. If you see the options, option A is correct. Now we have to find out the second option. The second option is we have to find out what is the total concentration at time t is equal to 0.3 microsecond. For getting the answer of this one, we have the second formula, that is this one. This is the formula which can be applied. So I am using the same formula, the total concentration of holes in n-type semiconductor at time t is equal to 0.3 microsecond, and this is equal to the initial concentration Pn naught plus the excess concentration, that is Pn of 0 into e raised to minus t divided by tau p naught. And tau p naught is given in the question, and we have already found out this value Pn naught, and this is equal to 0.45 into 10 to the power of 4 plus the concentration of holes, excess concentration of holes at time t is equal to 0, that is given here, and that is equal to 1.5 into 10 to the power of 13 into e raised to, this is t, and t is equal to 0.3 into 10 to the power of minus 6 because it is given in microsecond, and this tau p naught is given in the question, that is equal to 0.1 into 10 to the power minus 6. And if you solve this equation, then we are getting the correct answer, which is equal to 7.47 into 10 to the power of 11 per centimeter cube. And this is the correct answer for this question. Hence, this question having two answers. This is 1.5 into 10 to the power 13 per centimeter cube, the concentration of holes at time t is equal to 0. And the second is 7.47 into 10 to the power 11 per centimeter cube, the concentration of holes at time t is equal to 0.3 microsecond. Hence, the correct option from the given option in paper is A, and A is the correct answer.